I just had a few students during the break asking the same question. It's always about this term there, and they said, first of all, what does it mean to have both of them, that or the other, and which one do I choose? So I just want to clarify it again. If I took who is it? What is it? What is it? So if I took all the essential ones without these ones, I will have accounted for most of the ones here except the one here that's not part of an essential. And I will end up with a function, if I try to just get away with this, with a function that will take the value 0 for this particular combination of 1, 1, 1, 1. So I do have to account for this one. And then, as I showed, I can either take this group down here or this group down here. And what it really means is that you can choose either one of those groups. You don't have to include both. Now, there was a question, so if I come to an exam and I have a choice, which one do I write? Pick one. It doesn't matter which one, as long as they both have the same number of variables in them. If, for example, I was able to account for this one here with a larger group versus a group of 2, so if I had an option to either include this one as part of a group of 4 or as part of a group of 2, obviously taking the larger group will give me a simpler expression because it has less variables in it. In this case here, both options are groups of 2, which gives me 3 variables each. So I can pick either one. It'll give me the same complexity of an expression. If I, by the way, circled this on its own, which is something I could have done and still get the same result for the function, I would have added a, b, c, d term, but this one has 4 variables in it. So in a way, it's not as optimized as just picking one of the others. Does that make things clear? Does anyone still have a question? Okay. So what we've done up till now with K-maps, corner maps, we always obtained a sum of products out of the corner maps. Now, sum of products, by the way, that's another question that I had during the break. Why are we even doing this? Because corner maps will help us come up with a simplified 2-level circuit for implementation. So 2 levels mean either a sum of products or a product of sum. In K-map, as we've seen it, we'll always produce a sum of products. What if we want to use product of sums? Now, the difference, if you remember from last week, when we have a sum of products, we have one level of AND gates, and then the second level is one big OR gate, where if we have a product of sums, it's the other way around. We start off with the one level of OR gates to create the sums, and then one big AND gate to create the final product. So it depends if we have a preference to one or the other. You will see next week that we usually, in terms of circuitry, would like to work with sum of products better than product of sums. But for completion, there are technologies that sometimes you will use product of sums. I'll introduce this one. Now, in order to come up with product of sums, you can do it directly from the corner map in a similar, not exactly, but in a similar way to what the method we used before. It turns out that it's actually easier to find the sum of product expression like we've done it, because this is what you'll do most of the time, and this is what you'll get used to. And trying to do things in reverse starts to be confusing. So we will find the sum of products expression. And then, so we'll take the sum of product expression for the inverse of the function. And then we'll invert it using De Morgan to get the actual function back but applying De Morgan to a sum of product yields a product of sums, as we'll see in the example now. So we have some function that's specified as a sum of mean terms to begin with. And this is its corresponding conomer. Now we know how, if we were asked to come up with regular sum of products for the function, that's what we've done in the last hour. We know how to do this. And that's easy. Now in order to get the product of sums, we'll find the sum of product of the inverse of the function. Now what does it mean to find the sum of product to the inverse? It means circle all the zeros instead of the ones. So in a way, what you're doing when you're circling 0, you're saying the function will take the value 1 everywhere that I circle, which are the zeros, which is the complete complement of the function, of the same function with the ones. So we'll start off just like we've done before, finding the largest groups. And by the way, circular groups is something that you get used to very, very quickly. You sort of look at, because conomaps don't usually get any bigger than this, you usually get a very good idea of which ones are the largest groups just by looking at it. And you can see if you're grouping zeros, this will be one group of 4s, because we can't go any larger than this. There's another very obvious group of 4 going here. And then we still have a couple more zeros that we need to account for, and these will be, and we can wrap them around together, also in a group of 4. Now, as sort of I showed earlier, I could have just grouped them both together as a group of 2, just themselves, but it works to my benefit to group it in a larger group, even if I already, even if I'm including terms that were already in there. So this will now give me the complement of f. Now pay attention to the notation. I put a bar above the f because it's not the same function. And then I read this group here will give me a and b. Remember, a group of 4 will give me 2 variables. This group here, the horizontal one, will give me c and d. And the group that wraps around will give me not b and d. So this is a simplified sum of product expression for the complement of f. Now in order to get the product of sums for f, what I will do, I'll take this f complement and I will complement it again. So I put 2 bars over it. So the f complement will be a, b, or c, d, or not b, d. And then the whole thing will be complemented. Applying De Morgan, I will do it in stages. Applying De Morgan once will give me a and b inverted, and c, d inverted, and not b, d inverted. Then I can have another application of De Morgan for each one of those terms here to get not a or not b, and not c or not d, and b or not d, which is now in a product of sum form for the function f. Easy enough? Questions? Moving on. So we covered sum of product optimization. We covered the product of sums optimization. Now let's talk about incompletely specified functions. Sometimes functions operate on certain combinations of inputs. but they may not include all the possible combinations that we can have using some number of variables. For example, a function that operates on BCD code, so a function that takes one of the 10 BCD codes, will not use the codes that are not used for BCD. So 1010 all the way through 1111. There are valid 4-variable combinations, but our function will, if it works in BCD, if it works on BCD inputs, then you can assume that they will never be inputs to the function, and I will not need to account for them. So this is what we call a don't care condition. If we have some input combination that the function is not specified for, we call it don't care output. And then we can make the function to be either a 0 or a 1. And why would we want to do it? Because we don't actually care what the output will be, because the input should never happen. And therefore, we use whatever is more convenient to send it to either a 0 or a 1. Now we mark the don't care using an X symbol. And this will become a convention from now on. Wherever you see an X where you'd expect either a 0 or 1, that means a don't care condition, or a value that can be either a 0 or 1, it doesn't matter. Now we'll use the X's both in truth tables and in chronomaps. You may see them in data sheets. In fact, you will see them in data sheets. You will see them in Verilog HDL when we get to programming our hardware. So we can specify don't care conditions. So you know what the X stands for. Now, why does it help us? Because then when we have X's in the chronomaps, we may choose to include them in our groups or choose not to include them in our groups, depending on what will give us the simpler expression. As an example, here's a function, and here's a bit of new notation. So this function is specified as a sum of min terms, or those don't cares at places 0, 5, and 8. So if I had to draw a truth table for indices 0, 5, and 8, I would just put an X as the output, as the value for the function, and that means I don't care whether the output is 0 or 1. How does that help us? Because we can choose whether we want to include those X's in our groups or not. So one option, and again I want to make the largest groups possible. I'm still after grouping all the ones, possibly grouping the X's or the don't cares in there or not. So one option, I still need to account for this one here, and I do want to make the largest group possible, is to take this group here. Now in this case, I have accounted for all the ones. I accounted for 2 of the don't cares, which really will force them to be a 1 now when you implement the circuit. I'll show you. And I've got this X here, which is not accounted for, which will now make it a 0 when I implement the function. Alternatively, I could have another grouping, which will again take this column of ones there, but this time take this group of 4 here, accounting for this don't care, but not accounting for the other don't cares. It doesn't matter. In both cases, the additional group will be a group of 4, so it doesn't matter which one I'm choosing. Usually, we will try to maximize the size of our group. So if there's any combination that will give us a larger group, we would prefer this. In this case here, we will have the group here give us A and B. This group here will give us not C and not D. And this will be a perfectly good expression for this function, where if I use the other corner map, I will again have that A-B term from here, but now I will have or B not C term from the other group. Are these two functions equivalent to each other? They're not. Why? Because this one here will send these combinations, the 0, 0, 0, 0 and the 1, 0, 0, 0, to 1. So if I plug those values, I will get a 1 out of this function. Where if I plug them in this one, I will get a 0. Do both functions are value expressions for the given function? Yes. Because I don't care for these indices whether my output is a 0 or 1, I will try to simplify the function as much as I can. Now, you can do the very same thing, and this is, by the way, the same function that I just looked at, finding a product of sums expression for f. So just like before, I will find the expression for the complement of f. So I will start circling groups of zeros. Now, for example, this is to show you how good don't cares can help us. You can have this 0 here, and you start grouping it. You're looking around, what can I group it with? And then you realize you can actually go all the way up, group these, and wrap around here, and form a really large group that captures almost all of our zeros by utilizing those two don't cares. Again, once I include them in our group, those don't cares will be pushed to 0. So when I implement the circuit and I do put these combinations, the output from the circuit will be 0. There's no such thing as a don't care output for real. From a circuit, you either have a 0 output or a 1 output, which is a white lie because I will show you other outputs it could be, possibly on Friday, I think. Yep. As far as you're concerned, it can either be a 0 or 1. Now I have to account for these zeros as well, and I'm trying to look what's the largest group I can make them with, and this will be this one here. I couldn't go further up because if I want to double the size, I will go up and then I'll include this one, which is undesired. Now writing out my expressions for the zeros, the really large group gives us the term not B, or the second group will give us not A and C. Again, this is a sum of products. I really want my function in a product of sums, and this is the complement of the function. So the function will be the complement of this, which, taking the Morgan, will give me B and A or not C, which is in a sum of product of sums form. Now if you take this function, now we said this is an expression, a product of sum expression for f, which was given by this function here. And we said in the previous slide, we had the same function. And I'm trying to see whether this expression here is in fact equal to the expressions I got there. So remember we got now the expression B and A or C. Is it identical to any of them? To the right one, to this one. Now the reason why this one and this one are equivalent and this one and this one are not equivalent is because you can see that in this mapping here, I indeed took the exact complement of what I've used here, where this is something different. Okay. Any questions about don't care conditions? Right? New topic. Multiple level optimization. So up until now, with corner maps, what we were interested in is always a two-level optimization of a circuit. If you remember, last week we said we want two-level optimization because two levels usually give us the fastest circuit possible. Not necessarily the smallest one, but it will always have two levels of propagation delay. The alternative is to use a multiple level optimization. In multiple level optimization, we'll have more than two levels of gates, which implies more propagation delay because the signal has to go through more levels, and the more gates you have in the path, then the slower it'll take the signal to get to the output. But we might end up with a reduced circuit in terms of the gate input cost. Now, gate input cost sort of implies smaller gate input cost implies smaller number of transistors, which implies less area on the chip, which implies less power and less cost and so on, but slower circuit. So again, depending on what we're trying to optimize for. Now, the problem with the methods I'll show you now when we want to optimize for multiple level is that there's no systematic procedure to come up with optimum solution. And then comes the question, what is the optimum solution? Well, optimum solution depending on what you're optimizing for. As I said, there's different factors you can optimize for, power, size, speed, and so on and so on. But regardless of which one you're after, for multiple level optimization, there's no one way that will always give you the optimum solution. Similar in well, not similar to K-maps, where in K-maps you can always come up with an optimum two-level optimization. And this could sometimes be a bit frustrating, especially if you've tried those tutorial questions and you're not quite sure what's the next step, and you keep trying, and then eventually get to something that looks like it may be optimum, but there's no absolute way to know this. So what I'll do now, I'll give you a couple of methods to optimize for multiple level. There's a few more. There's further methods you can use to optimize it even more, but they do start to get quite complex and not so intuitive. I chose the two most intuitive methods to show you. If you are interested further, the textbook for this course and other textbooks will tell you wonders about how you can keep optimizing it. Now, the sort of stuff I'll show you now, which is factorizing and decomposition, are really a bit of a specific case of what we'll talk about next week, which is hierarchical design, where in next week we will start putting things into black boxes and give them interfaces, so tell what the inputs and outputs to the black box is without actually caring what's inside the black box. So we'll talk about this now, and then you'll see next week when we talk about hierarchical design how these two things are related. So we'll start with factoring. Factoring is really just taking a sum of product of some expressions coming possibly from a corner map, and then pretty much factorizing common terms out. So for example, if I have the function g that has a gate input cost of 17. Am I on yellow? I'm on yellow. Do you want me to go through how do I come up with 17 out of the circuit, out of this expression? Yes. Yes. Let's do that. Okay, so we have some long expression that's not actually given as a circuit. The gate input cost, by definition, implies how many inputs to all the gates in the circuits are going to be. Now, one way is to draw the circuit, but it's a nightmare for something of that size. The other way is actually to come up to understand what circuits we do have, or what gates we are using. Well, for this expression here, this term will use an AND gate, but it'll be a 3-input AND gate. Now, someone asked me before when we do gate input cost, should we assume we only have logic gates with 2 inputs, or can we assume as many inputs as we want? Usually we can assume any number of inputs that we want. In reality, there are gates with 2, 3, 4, 5, 6 inputs. Once you start going over 6 inputs, the circuits start to fail. And we'll see how, in week 12, we'll see how we actually build those circuits out of transistors, and I'll explain why we can't have too many inputs to a gate, why we can't go infinitely many inputs as we want. Usually most gates in reality will have 2 to 4 inputs. You can find gates that have 5 or 6 inputs. Above that, it's quite rare. For the purpose of counting gate input costs and all the theory that we do, we can assume as many inputs to a gate as we want. In this case here, we have a gate, an AND gate with 3 inputs for the A, B, and C signals. Similarly, we have 3 inputs here. This is not an actual gate because we're not doing any operation on this literal. We'll have another 3 input gate here, another 3 input AND gate here. And then these gates will create all the terms, and then we need one OR gate that will OR all 5 of these terms together. So counting, hopefully I get to 17. 3, 6, 9, 12 plus 5, I get 17 for the gate input cost. Now I want to reduce this number, and then I'll start factoring common terms. So from these first 2 terms, I can factor out the common AB and then have C or D. The E stays. From the other 2 terms, I can factor out A and F and end up with C or D. Then I have a common factor of C or D, which is here, which then I can combine AF or AB. And the E still stays on its own. And I can then take the A out of the brackets and leave it on its own. Counting how many gate input costs or how many gate inputs we have for this new circuit, we follow the same procedure of realizing this is 2 input OR gate, 2 input OR gate. Then we need a 3 input AND gate, and then another 2 input OR gate. So 2, 4, 7, and 9, and I get a gate input cost of 9, which is almost half as many gate inputs as I have originally.
For the 17, why don't all the A's just count as one input cost? Like, because I know they've all got in separate gates, but in a circuit they would all come from one voltage source.
Yeah, so this is why, for example, what we're counting here, we're not counting the number of literals, we're counting the number of actual inputs to the gates. If you want to imagine, for example, this first term here, this will be translated into a 3 input AND gate. And then the second one, which still has the literal A in it, but it will be a separate gate altogether. So that's another 3 there. All right, so and then you can ask something like, all right, well, we have AB and AB in both of them. We're already ending them together. Why do we need 2 separate AND gates? Well, this is exactly what we're doing when we're factoring. When I give you an expression, and I usually say, assume that the function followed the expression exactly as written, I count the gates as I count the gate inputs as I just did. You can factor these things out, which is exactly what we are doing, and then we can say all those A's that are ended with everything else, can be ended at the end with everything else, which is actually the term that we are reaching at the end. And then when we do the gate input cost, we are getting a reduced cost. I think that's what you asked?
Yeah.
Sort of? Okay. I think you also said A was just a signal. Why are we accounting for it? Something along those lines?
In the first one,
Yeah?
it's just one signal, but you're accounting for it 4 times. So in like an actual...
But I'm not counting the signals. I'm counting the inputs to the gate. So each one of those signals, it might be sort of one signal source, and then it branches to the different gates. It probably does. But in terms of gate inputs, I have 2 separate gates. So I have to count the inputs to both of them. Does that make sense?
Yeah.
So? Or I'm missing?
Why you counted them multiple times?
Yeah.
Like, why would it never be minimized? Like in any circuit, why would input cost never be minimized?
What do you mean, why would never be minimized? We are trying to minimize it.
Yeah, but in the previous one when we were minimizing the propagation time, and we didn't account the input cost, why now would we not have done it for the same time? Or is it just implied because it's POS?
I hope I understand what you're asking. When we done the 2-level optimization, we're not actually optimizing the gate input cost. We're not. You will get a larger circuit than if you tried to do it here. I mean, this is a 2-level circuit. The first line is something that possibly came from a K-map. And it's only consisting of one level of AND gates, another level of one big OR gate. So the propagation time will be minimal because you're only going through 2 gate levels. But the gate input cost is actually high, where once we start factoring things out, you actually go through several levels of gates. You reduce your gate input cost, but you're trade-offing, is this a word? Trade-offing the propagation delay. So depending on what you're optimizing for.
Well, what would minimizing the gate input cost actually save you in a circuit in terms of power? Or
so gate input cost is usually a good indication of the number of transistors you have. It's not a one-to-one mapping, but it's a good indication. When you minimize the gate input cost and therefore the number of transistors, you're saving, first of all, space on the chip because you need less transistors. You also save power because you don't need as much switching in the transistors. The smaller the chip is, the cheaper it is, but by far. Even a slight reduction in chip size will make the chip much cheaper. So it is significant in that way. Again, it depends what you want to optimize for. For example, Apple with my iPhone 3G did not care about speed at all. I can testify for this. But they claim that they optimize for power, which I'm not even sure for this. But obviously, they do optimize for different things. All right. Other questions? Another way to optimize for multiple level optimization is to use what we call decomposition. Now, the idea is in decomposition is to find common terms in my overall circuit that are being essentially used in several different places in the circuit, and then come up with the idea that we can calculate them only once, and then use the output from that calculation in several different places in the circuit. A very sort of the extreme example of this is when you use negation of variables. Suppose you didn't have the complements of variables available to you, so you do need to pass them through an inverter. So if you had the signal A, you pass it through an inverter to get not A, but then you can use this not A as many times in the circuit as you want. So you don't have to put an inverter every time you need not A, it's enough to calculate it once. And extending this idea is the idea of decomposition. So again, let's take some really complex function that has a gate input cost of 26. and it's left as an exercise to actually calculate it, the 26. We start off with what we've done before. We factor the expression. So you go from this expression here, which for this one have a common a variable. So we take the a out and left with this plus the last term there. And then we can group together, we can take out the naught c in one term and then the naught d in another term, and then figure out that what we get in both of them is e or f, and factor this out as well. So far nothing new. We're just doing factoring just like we've done before. So we already reduced the function a little bit. So this is up there. This is the expression I just showed you after factoring. Now we will define two new terms, x1 and x2, where x1 will be c and d, x2 will be e or f. Each one of those terms cost us 2 gate input costs. Now you'll see that it will be very useful to then see that not x1 will be using de Morgan not c or not d, not x2 will give me not e and not f. And then I can actually rewrite the function g, which is up there, in terms of x1 and x2, or their complements. So this a here is the same. This will now become not x1. This is x2 because we defined it, where is it? We defined it to be e or f. And then we can use the CD here to be x1, not e, not f, to be not x2, and rewrite it in this form here. Now, how do we calculate the gate input cost of this expression? Well, we have to understand what is it made of. So we sort of have little circuits on the side that make the expressions x1 and x2 for us. We do have to account for them because these are gates that we are using. Each one of them, we said, will have a gate input cost of 2. Now, to come up with the inverted version of each one of them, we have to pass it through an inverter. So this will add another gate input cost because an inverter has only one input. So this whole term here, if we just treat now x1 and x2 as variables, we have a 3-input AND gate, a 3-input AND gate here. We have a 2-input OR gate, so this will give us 8, plus, because we're using x1 and x2, we use to generate the 2 to generate x1, the 2 to generate x2, and then the inverter input, so we had 2 of them, to come up with the overall number, which is 14. Does that make sense?
Can you explain how, I know we got the 8, but where'd you get the 2 to 1? What'd you
The-
represent from the x1?
This one?
Yeah, this one, yeah.
Okay, so these come from generating x1 and generating x2. Because these, huh?
Are they unknowns or?
No, they're not unknowns. They're, it's not x as in don't care. It's x as the definition I made here. I could have called it T1 and T2. If you want. All right. Any questions about multiple level optimization? If not, then let's get out of here. All right. That's enough for today.